Okay, I'm going to do another video today to finish off the revision section on forces, which is a year 10 topic normally in IGCSE. So thanks for watching all the other videos. If you've already watched them and you've given me a thumbs up, a like, that would be great, because the more likes and shares we get, the further the channel will spread, and once we get enough subscribers, the channel should become self-sufficient in terms of financially, that it will make it worth the while of making videos in the future. So we're up to 500 and something subscribers, 570 I think we're up to today. We've had 30 something subscriptions in the last 7 days. And so today's video is on the turning effect of forces about a pivot, and these turning effects are called moments. Okay, so the turning effect of forces, how do you analyze turning effects mathematically? That's one thing you need to know. And what is the moment of a force and how is it calculated? Okay, so these two are really the same thing. So the first thing you need to look at here is the moment of force. I nicked it from the internet. So if you have a spanner and you're trying to tighten a nut, or you're trying to untighten a nut, you would need to turn it, and that turning effect of the force is called a moment. Okay, and you would take the moment around the pivot or the turning point. In this case, it's the center of the nut. Okay, so if we want to know that, we need to know the force acting, which is the man's hand, his arm pulling up at this angle, and you need to measure the distance of the force to the point about which it's going to turn, usually. Okay, now obviously if he held the spanner further along, he would get a bigger distance, and a bigger distance would increase the turning effect of the force. So the moment or the turning effect of a force is called the force multiplied by the perpendicular distance from the pivot, between the pivot and the line of action of the force. That's what we call it. The line of action of the force is the direction the arrow is pointing. So you're on a perpendicular distance to the point about which you're taking the moments. Okay, so basically in simple terms, a moment is a force multiplied by a distance, so the unit will be a Newton meter. Okay, now you do sometimes have forces multiplied by distance when you're doing work done, and then we call it a joule. If the distance is in the same direction as the force, that's work done. In this case, although you are working hard, the effect of the force, which is at right angles to the distance, is not called a joule, it's just called a Newton meter. So moments can either be classified as clockwise or anti-clockwise. So this one is anti-clockwise because he's pulling upwards, so he's going against the direction that an analog clock would make the circular motion. Okay, so the force F exerting an anti-clockwise moment through the spanner on the nut. Okay, so this is how you need to understand what the moment of a force is. So for example, if you're trying to open or close a door or use the spanner, you are using a turning effect, because for opening and closing a door, the door has hinges, which is the equivalent position of the turning point. So that would be the equivalent of the pivot, or the fulcrum, which is also another word is used. The size of the moment, as you know, is equal to the force in newtons multiplied by the perpendicular distance from the pivot. Okay, perpendicular distance to the line of action of the force. That means the arrow that's been drawn. So if the arrow is at an angle, you need to be careful how you determine what the perpendicular distance is. Okay, so for IGCSE Edexcel Physics, you need to learn this equation. For those of you doing double award and doing the physics for it, this will not be in your exam. This comes in paper 2, which is for physics IGCSE students only. So to calculate the following turning moments, so if you have a plank of wood and the pivot is at there, they haven't shown you the whole plank of wood, but just say that's the point about which we're going to calculate the distance. And you've got a fox standing at the other end, and if the distance of the fox to the pivot is given as 5 meters, and we know the weight of the fox, yeah, in this case 100 newtons or 10 kilograms, 100 newtons, then can you work out the turning effect due to the fox? Well, it'll be the force is 100 newtons, the perpendicular distance from that line of the force. Remember, the line of the force is up and down, so the distance is automatically perpendicular. So it's 5 times 100, it will be 500 Newton meters. Then if you do the same, if you have a different animal, the bear is coming on the other side, yeah, perhaps, and the bear's distance is 2 meters from the pivot, yeah, or the fulcrum. That triangle underneath is called the fulcrum or the pivot. And the bear obviously weighs more than a fox, and they've claimed it's only weighing 200. So what is the moment for the bear? It's going to be 200 times 2, so it's 400 Newton meters. This one, the fox is going clockwise, and because here's the center of the clock, it's turning it clockwise. From 3 o'clock, it will go towards 4, and the bear is going from 9 o'clock down towards 8 or 7 on the other side of the clock. So this is going anti-clockwise against the clock, and this is going with the clock, so it's clockwise. All right, so that's the basic definition and how you calculate moments. The spanner works, and so do these seesaw examples with the animals. Now, if we actually try to balance the fox against the bear, and this time the fox is only 2 meters from the pivot or the turning point, yeah, clockwise moments are 2 times 100, that's 200 Newton meters, and the bear is also 2 meters. Well, obviously the fox will not be able to balance the weight of the bear because the distances are the same. So is it in balance? The answer is no. So this seesaw will not be in equilibrium. What will happen? So the anti-clockwise moments under the bear, and this is what you've got to do, the sum of the anti-clockwise moments, over here they've written it as total. Often in physics we call it the sum of the anti-clockwise moments because you may have more than one weight adding to the anti-clockwise moments. In this case it's just the bear, yeah. So the sum of anti-clockwise moments is 400 Newton meters, and the sum of the clockwise moments is 200 Newton meters. So the anti-clockwise moments are greater than the clockwise moments, so that means the turning effect will be 200 Newton meters anti-clockwise. Okay, the anti-clockwise moment is bigger, so the seesaw will turn anti-clockwise. So these two animals are not in equilibrium when it comes to turning effects. Okay. All right, so what about, can these two be balanced? Can the bear be balanced by the man? If the man is 800 newtons and the bear is 2,000 newtons, that's about 200 kilograms. Yeah. What distance must the bear be standing where its center of its mass, yeah, the center of its body is where we draw the weight from, and there'll be a separate section on that of how we just determine the center of the mass. So what distance must the bear be from the yellow fulcrum in the middle to balance the moments anti-clockwise that is produced by the 800 Newton man or humanoid? Okay, so the man is 800 times 5, that's 4,000 Newton meters. So obviously that makes it easy. 2 times 2,000 will give you the equivalent turning effect to in the clockwise rotation. Okay, so the answer is, can they be balanced? The answer is yes. How? By the bear not moving and staying at 2 meters from the pivot. Okay, so they haven't given you the answer here, but it will be 2 meters. Okay, so I hope that makes sense. So you can have, in the previous question, you have the bear is not being balanced by the fox, but over here the man standing further away from the pivot is balancing the heavier bear, as long as the distances don't change. Okay, so these are seesaws used often by children in playgrounds. So what about these? Are they going to be balanced or unbalanced? Well, obviously the one on the top diagram, there's no weight on the right clockwise to balance the anti-clockwise moment of the single weight, yeah, at 1, 2, 3, 4 distance units. So this will be 1 weight times 4 distance units. So 1 weight unit times 4 distance units. let's call them 4 weight distances. Yeah, so 4W we'll call it. So let's call each of these 4W, and over here you got 0. Okay, and over here you got 2 at distance of 2, so that's 4 turning effects, 4W equivalent, because 2 times 2, 4W again, and this time is 1 weight times 4, so it's 4W. So this one will be balanced. Yeah, 2 at 2 and 1 at 4 distance units will balance each other out. Over here you got 1 at 4, yeah, and 1 at 1, so that adds up to 4 plus 1, 5, and this will be 4 because it's 2 times 2 distance. Okay, so you multiply the weight, in this case 2, by the distance 2, this will only give you 4. So this one would balance this one on its own, but because you've also got this one, the anti-clockwise moments are greater than the clockwise moments, so it will be unbalanced. Here you've got a 4 and a 3, yeah? This one's 4 units away from the fulcrum, yeah? If you count these black lines, 1, 2, 3. So this is 7 turning effect, 7W, shall we say, multiplying the distance by the weights. And here you got 4 and 3, 7. So this is 4 and 3, 7. This is 4 and 3, 7. So the fourth one is also balanced in terms of the sum of the clockwise moments will be equal to the sum of the anti-clockwise moments. Okay, or the total anti-clockwise moments is balancing the total clockwise moments. Okay, remember, on the right is clockwise, on the left it's anti-clockwise. So then now that you know how to calculate turning effects clockwise and anti-clockwise, can you calculate the missing quantity? In this case, the weight on the right hand side. So I'm going to give you a little bit of time to think about it. Okay, so the first thing I would do is look at the anti-clockwise moments, because we have all the data. 2 newtons, they're calling it, so it's becoming a little bit more scientific, and 4 meters. So that's 8 Newton meters anti-clockwise. So to get 8 Newton meters to ensure that it's balanced, this means this weight must be 4 newtons. Okay, so this would be 4 newtons. Over here we got 5 times 2, 10 Newton meters anti-clockwise, and here you must have 3, and this one must multiply to 10, so it must be 3.33 recurring meters. If this was 3.33 meters, it'll more or less balance the 10 Newton meters on this side. Okay, and over here you got 5 newtons and another 5 newtons, and on this side you got 15 times 2. So clockwise this time we have all the known values. That's 30 Newton meters here. 20 comes from this one because it's 5 times 4. Yeah, so we want 30 in total. There's 20. That this one must add up to 10 when multiplied. Was multiplied to 10 when you take into consideration the distance. So this distance must be 2 meters for it to be 20 plus 10, 30, 15 times 2, 30. So if you get the calculations right, you'll be able to work out the missing quantities. Okay, I hope that helps. This is the kind of skill you need to be able to calculate missing masses or missing distances for the IGCSE exam in paper 2 of physics, okay, in Edexcel. So here is a recap. If you got 30 kilograms at 1.2 meters from the fulcrum and the man is standing at 0.4 meters, and if they're balanced, can you work out the mass of the man? I'm sure you can. Yeah, 30 times 1.2, what's that? 30 times 1.2 is 3.6. Is that right? 36 Newton meters. So what times 0.4 must be 90 kilos. The man must be 90 kilos. 90 times 0.4 will also give you 36 Newton meters. I hope I got that right. I'm doing it in my head. Okay? If not, tell me in the video if I made a mistake. Okay, so this is coming towards the end of it, and this is what we talked about. The center of gravity is the position through which we can consider the weight of an object to be acting through. Yes? So it's really the center of the mass. Yeah? So we call it the center of gravity. It can also be called the center of mass. Okay? So where would the center of gravity for these objects be? For the man, it will be like near his belly button. Yeah? It may not be exactly. For the hammer, it will be towards the metal end because this is more dense. So the center of mass may be somewhere over here. And you could try to balance it at that point, and that's how you find out where the center of mass of an object is. Because obviously if you got, say you put your finger underneath the hammer, you can see, oh look, you managed to get it balanced, and the heavier metal end will balance the longer bit on the other side. Yeah? And these, I don't know what they're called, that they put in, can't think of the word. These things that they put in babies' cots to keep them amused, and they vibrate. Obviously the center of mass must be in the middle, so the planes on the right are balancing the planes on the left, and so on. And the plane on each side is balancing the weight of the other one, and one is in the middle. So this one is balancing this one is balancing that, and this one's right in the middle, so it doesn't really take part in the balancing because it's actually hanging through the center of gravity of the whatever it's called, contraption. So then I've asked you a question at the bottom. What about the center of gravity of a uniform beam, like the seesaw that we were looking at before, or like the plank of wood? So if you've got a plank of wood and it's a uniform thickness and uniform density, we have to assume that the center of the gravity of the plank of wood will be its center of its length. Okay? So if it's a non-uniform beam, you'd have to treat it a bit like the hammer and work out where is the balance point where the moments on the right will balance the moments on the left. Okay? So why am I saying this? Because sometimes you'll get problems in physics to do with also considering the mass of the plank of wood has to be also considered as potentially creating a moment either clockwise or anti-clockwise. Okay? A bit like on this child's toy, that these plastic lengths, if they've got different lengths on each side, it will topple towards the side which has the longer part. So they've put them exactly, they've hung it through the center of these two rods, okay? Because then the center of mass is acting through the center, and therefore its mass is evenly distributed on both sides. So the clockwise moments and anti-clockwise moments will balance. But if they don't, then you also need to consider the weight of the rods in this case, or the beam if it's a seesaw. So here would be a kind of question where a man is walking along a plank of wood which is hanging over a cliff. Okay, so here's the cliff, there's the plank of wood, and obviously the center of mass of this plank of wood will be right in the center if it's a uniform plank of wood. That means same thickness and same density throughout. Okay, so if the man then walks, and if he's foolish enough to go over the edge of the cliff, or over the on the plank over the edge of the cliff, would he be safe? So remember, the mass of the plank is acting here, so the weight of the plank could be considered to be halfway along the length. So there's one weight pulling it down here. Right now, the man is also pulling it this way, and if we wanted to make sure that it's not going to topple, both of them are anti-clockwise. If you think of it in terms of, say, over here, taking moments about the edge of the cliff, both of them are adding to the anti-clockwise moment, and the only bit that's adding to the clockwise moment is the bit that's hanging over the edge, and it won't be enough to cause a problem for the man. But how far can the man walk over the edge of the cliff? Yeah, that means over this bit here before the plank tips over. Well, that all depends on the weight of the man and the weight of the plank and the distance that's overhanging. So it's quite a complicated thing to do. But if you follow the rules, which is the sum of the clockwise moments about the point, say you want to take the moments about this point, you could, as long as you got all the distances and the weights. If the sum of the clockwise moments is equal to the sum of the anti-clockwise moments, it will stay in balance. As soon as the clockwise moments goes greater than the anti-clockwise moments, the man and the plank of wood will start to turn and fall down the cliff. Okay, so the man's weight is 800, yeah? And he's going to move, so we don't know where he's going to end up. And the plank's weight is only 200, so the man's heavier than the plank. Then it could be even riskier. But if you had a heavier plank, it would be safer, because most of the plank is on the land, okay? It's not hanging over the edge of the cliff. So we know the two weights of the plank and the man, and we know it's 3 meters, and we know that the weight, the plank weight, if it's uniform plank, is 1.5 meters along the plank, okay? And then we know that 1 meter is hanging over the edge, so we are now getting enough information to try and analyze it. So right now it's all safe, because the weight of the plank is here, the weight of the man is here, and they're both adding to the anti-clockwise moments, and the only thing that's hanging over is the 1 meter of wood, which is less than, it's only a third of the weight of the wood, so it's not going to fall over, okay? But if the man foolishly walks over there, how far in centimeters can he go beyond the edge of the cliff before he topples the whole thing? So now if he's at this distance, his weight is 800 here through his center of his body, or his center of his gravity, or the center of his mass. So 800 newtons here. Unknown distance there, let's call it d. So 800 times d here. And we know that this distance is, the plank's weight is 1.5. And we know the distance from the center of the mass of the plank, 200, to the edge, it must be 50 centimeters, okay? Because it's 1 there and 1.5 to the center. So 0.5 times 200. So anti-clockwise now is all due to the plank, yeah? Taking moments about the toppling point. So 200 times 0.5 will give you 100. That means the man, 800 times d must equal 100 Newton meters. And I think you'll find is 12.5 centimeters, or 0.125 meters, if I've done that correctly. Unfortunately, on this slide, I haven't put the answer, but I've just done it in my head, and it's going to be 0.125 meters. And if you want to have a go at doing that with the clockwise moments and anti-clockwise moments, this is a higher level question, okay? Good luck. All right, so if he goes over 12.5 centimeters beyond the edge, that's what will happen to him. So here's another example of a bridge, for example, that's held up with cables at the two ends, okay? So it's a floppy bridge, and you're going to go up across it. So then we have a car. So as the car drives along the bridge, how would the upward force on each beam change? So on each, these are the beams they're talking about. So obviously when the car is at this side, this beam is going to take more of the weight than this beam. But at the beginning, the car was on this side, so this one will be higher to start with, and this one will be higher to finish with. Now, how do you tackle such problems in physics? Okay, well, if you know the distance between the two beams, as they call them, yeah, and you know the weight of the bridge is 500,000 newtons, and you know that if it's uniform, they haven't mentioned uniform, but it's important that we have these terms already defined on to be able to do that. Sorry, I just had a phone call coming through. I've stopped it. So let me see if I gather my thoughts. If the car, then the center of the mass of the car is 3 meters from the edge on the left edge, and the weight of the car is 10,000 newtons, but the bridge is 500,000 newtons, the bridge's weight acts 10 meters from here. The car's weight acts 3 meters from there. So you to find out what the size of the force in here is, for example, you could take moments about this point, because all the distances are known to this point. So you can take moments about whichever point you want. So if I want to find the force due to the car as it is now 3 meters from the left side, if I want to find the force on this beam which is acting upwards, yeah, taking the weight of the bridge and taking the weight of the car from that distance, all I've got to do is to work out, well, this one is, the weight of the bridge is clockwise about this beam, so is this, yeah, but this one is pulling upwards, so the weight of the beam is down, the weight of the bridge is down, the weight of the car is down, so both of these are trying to turn this clockwise at this point, yeah. So this one will be 3 meters times 10,000, yeah, the turning effect of the car, and this will be 500,000 times 10 meters because it's going to be halfway along the length of the bridge, okay? So 500,000 times 10, that's 5 million, and this one will be 10,000 times 3, so you've got to add them together, and then we know that this force multiplied by 20 must balance the clockwise moments. And once you know that, you can work out the force here times 20, and you have enough information to be able to do that. So F, let's call this one F times 20, must equal 3 times 10,000 plus 500,000 times 10. That will be the equation. If you stop the video and listen to what I've said, if you can write that out as an equation, you'll be able to work out the missing F. That's the only missing value. And once you've found the F, yes, you can then do the same. You could work out, well, how much there must be here, because the sum of the weights downwards is 510,000 pulling downwards, and whatever this force upwards is, and this force upwards, they must also add up to 510,000 newtons. Okay, so it's quite a complicated question, and this is useful for students preparing for A-level. Okay, this is more higher GCSE and introduction to A-level. I hope that made sense. If I have a chance, I will write out the solution and put it in the comments. Okay, so thanks for watching. This was taking you through the simplicity of moments being force times distance, all the way to the complexity of problem solving, which can get more and more difficult depending on which level of physics you're studying. So I think this is a useful video for GCSE and for students starting A-level. So don't forget, please give me a like for every video that you learn something from. So a like means you're paying me back for the knowledge I'm giving you. Share it with your friends so we get more subscribers, yeah? And make sure you subscribed if you haven't done so already, to be notified when the next video is going to be made. Right now, because I'm on half term, I'm making 1 or 2 or more per day. Okay, that's it for me. Thanks for watching. Bye for now.